Hello everyone. In this session, let me continue the theorem on outer measure. Here I have a statement. The outer measure of an interval in R, where R is real number, is equal to its length. Meaning is, as I already told you, outer measure is represented by m star. So we have to prove m star of an interval in R. Suppose if I is any interval in R, then we have to prove outer measure of that particular interval is equal to its length, in the sense length of that particular interval. We have to prove that measure of any interval in R is equal to length of the same interval I. Fine. Now before getting into the theorem, let me revise the concepts where we have already studied the properties of outer measure of a set. Right? Seventh property says that m star is translation invariant. M star is none other than an outer measure. Please go to the previous video. I have explained clearly while explaining the translation invariant property of an outer measure. So as per that property, if for every epsilon greater than 0, for any open set A and In is any open interval in A, then I can write summation length of any interval In is less than m star A plus epsilon. Fine. I am repeating once again. This is as per the translation invariant property of an outer measure of a set. This property I have explained clearly in property 7 of outer measure. So if m star is an outer measure, then there exists for epsilon greater than 0 for any open set A and In is any interval in that particular open set, then I can write summation length of any open interval is less than m measure of an open set A plus epsilon. Fine. You just remember this property. And one more thing is, suppose if AB is an interval, either it is open or closed interval, length of an interval will be B minus A. And we can write that any element in this particular interval can be written as, in the sense, suppose if I am going to take, like say, let me take interval I as like closed interval or else open interval, whatever may be the case, then we can write the same as AB is subset of A minus epsilon, comma A plus epsilon, or else, I'm sorry, the last term is B here. So I have to write B plus epsilon. I'll give you one more example. Just listen to me. Suppose if I have an interval, I say PQ. Fine. In general, then I can write this PQ is always a subset of P minus epsilon and Q plus epsilon. So the value behind this, epsilon is very small quantity, the value behind this and the value behind Q, next to Q. So that is why we can write any open interval is subset of P minus epsilon and Q plus epsilon. Fine, you just remember this basic concept to prove this theorem. Now coming to the proof of the theorem. The outer measure of an interval R is equal to its length. We have to prove outer measure m star of this interval is equal to length of the same interval. Now there is two cases we can discuss. Case 1 is that suppose if an interval I is closed interval, I have clearly mentioned here, is a finite closed interval, CLOSED, closed interval, I can say closed interval in R. Then as per the definition of translation invariant, there exists for epsilon greater than 0, this interval can be written as subset of A minus epsilon B plus epsilon. Now let me take measure on both sides. M star of closed interval AB is less than or equal to, when I take measure as per the monotonic property, this subset will become less than or equal to, and we have to take, as soon as I write measure here, I have to take length here, length of A minus epsilon comma B plus epsilon. So after simplification, I'll get this value as length is B plus epsilon minus A minus of minus will become plus. So that I'll get B minus A plus 2 epsilon, right? So clearly I can write m star of AB is less than or equal to B minus A plus 2 epsilon. Fine. Anyhow, epsilon is an arbitrary quantity. We can neglect it. So I can write m star of AB is less than or equal to B minus A. Is it clear? Now further I have already told you that length of any interval AB is B minus A. See here, suppose if I have an interval AB, then length of this particular interval I is given by B minus A. So I can write B minus A as length of an interval A. Fine. So I'll write it once again. M star of AB is less than or equal to length of an interval. I can write. Fine. Now let me take this as equation 1. Fine. Now I have already told you, as per the translation invariant property, we can write summation. We can write summation length of in is less than, since I have chosen an open set A here. In this particular case I have chosen open interval I. So I can write length of in is less than measure of I, interval A as per the standard definition, but I have chosen interval I, so I have written m star I plus epsilon. Let me take this as equation 2. Now for since epsilon is greater than 0 and it is anyhow arbitrary, now for if this is the case, then there exists a countable collection of interval, open interval in R, in such a way that I can write a closed interval AB is subset of n is equal to 1 to infinity in. Fine. I'll repeat this statement once again. This is as per the translation invariant property. Since epsilon is very small and moreover it is a positive quantity, so there exists an n number of such intervals in a real number line. Fine. In such a way that this considered closed interval, whatever the interval I have chosen here, that will be the subset of all those intervals in R. Am I clear now? Now, and also as per the property I can write n is equal to 1 to infinity, length of in is less than or equal to, I am writing with reference to equation 2. See here, n is equal to 1 to infinity, length of in is less than or equal to, measure of I is none other than, measure of I is none other than interval AB. I have chosen interval AB here, plus epsilon as it is. I'm repeating these two steps once again. This is as from the translation invariant property. If that was the case, then there exists, epsilon is anyhow arbitrary and it is positive quantity, so I have written epsilon greater than 0. And there exists such a closed interval, n number of intervals in R, in such a way that this interval will be a subset of union of all these open intervals. Meaning is this, suppose if I have an open interval, we can find n number of closed interval within this open interval. So that is why I have written it is subset. Now equation 2 will become m star of I is none other than closed interval AB. So I have substituted here plus epsilon as it is. Now by Hein-Borel theorem, you are already familiar with this Hein-Borel theorem in real analysis as well as topology. So Hein-Borel theorem states that being it is closed, it is a closed interval and bounded set. So if it is the case, then by Hein-Borel theorem, I can say I is compact. Hope so you remember this. Anyhow, I'll tell you once again. Hein-Borel theorem states that if any interval is closed and bounded in a real number, then it is compact. Now look at the interval I have chosen is closed interval AB. Fine. Now this interval AB is closed interval I have chosen. So as per the Hein-Borel theorem, it is closed and bounded. The values in between the closed interval AB is bounded in R. So I can say by Hein-Borel theorem, the chosen interval I is equal to AB is compact. Is this clear? Now, if this was the case, let me write this statement here again. I have considered this again, subset of n is equal to 1 to infinity in. Fine. Now I am going to choose an element A in this particular closed interval. Let A belongs to this closed interval, which is subset of n is equal to 1 to infinity I. I'll change the suffix just for your understanding. So I have given I is equal to 1 to n here. I have chosen one of the element in this particular set. if this is the case, I have already told you, we can have, as per the statement of first theorem, we can express it as countable union of open intervals. So A belongs to, I have chosen A, which is one of the element. So I can write A belongs to open interval, say A1, B1. So I have already told you, since it is a closed interval AB, there exists n number of open intervals between this. So I can choose one of the element which belongs to A1, B1. Fine. In such a way that this element will be in between A and B, in the sense A1 less than A less than B1. Fine. Similarly, let me choose one more element, say B1, in such a way that B1 belongs to an interval A to B2. See, I have chosen element A here. Similarly, B1 I have chosen A to B2. Why? Because I have already chosen B1 here. So A to B2 I have chosen in such a way that B1 is in between A to B2. Fine. I have chosen an element in this particular closed interval which consists of n number of open intervals. So I have chosen an element A in such a way that that element is in between these two values and B1 is again in between these two values. If this process continues so on in such a way that, let me take one of the element Bj minus 1 belongs to, generalized case I am writing Aj Bj, open interval Aj Bj. B1 is one of the elements. So if you go on continuing this process, let me take one of the element Bj minus 1 in Aj minus Aj Bj in such a way that this element is in between these two values, in the sense Aj less than Bj minus 1, which is less than Bj. Clear? Now, since what I have told is union of I is equal to 1 to n, In is the collection of intervals. Fine. So collection of intervals, then what I have assumed is In is collection of finite number of intervals, in the sense there should not be infinite number of intervals. So if you go on selecting the elements from that particular interval, this process should be terminate after some steps, say k number of steps, it should terminate. This will terminate only when, I'll continue the same here. See, this will happen, this statement will terminate. See here, union n is equal to 1 to infinity, In is finite interval. So this should be, the process of choosing element from this particular interval should terminate. Why? Because it is finite. So up to n, suppose if I have say n number of elements, you can stop at choosing nth element. Fine. So it should terminate at some particular stage k. So this will happen only when some particular last element, say B, belongs to that particular interval Ik, which belongs to AK, BK, in such a way that B is in between AK and BK. I am repeating once again. See here, I have chosen an element B1 which is in between A to B2 and Bj minus 1 which is in between Aj and Bj. So this process has to terminate until certain stages, say K. I have chosen that element as B in that particular interval Ik, such that that element is in between AK and BK. So that is the reason I have written like this. Now let me consider a length of that particular interval In. So clearly that should be greater than or equal to I is equal to 1 to k length of an interval I, in the sense n is a largest interval. Fine. Where I is a smallest interval. I have chosen here. See here, open interval I have chosen in the closed interval. So n is with reference to the closed interval. Look at the statement here. I have chosen the value n with reference to closed interval. Whereas I have chosen the value I, in this step, I have chosen the value I with reference to an open interval within the closed interval. So that is the reason n is always greater than length of this interval. Now, as per the simplification, I can write this as, see here, A, it is just the difference length. When you are going to talk about length, it is just the difference of a particular particular endpoints of a closed, open or closed interval. Now, length of I can write as, say, BK minus AK. Length of this last interval, and just beside that, just behind the particular interval, what we have is BK minus 1 minus AK minus 1 plus so on. This process continues until the last element B1 minus A1. So this is what the first element is. see here, since I have chosen A belongs to A1, B1, this will be the first element from the last. So when you continue this process, you will get a last interval, say AK, BK. So when you're going to take a length of that will be BK minus AK. Just beside that, you will get K minus 1. When you go on adding all the lengths, you will get B1 minus A1. That will be the end point. Fine. Now I'll rearrange this in such a way that BK I'll keep here. I'll combine these two. AK minus BK minus 1. I'll combine next two. So it will be AK minus 1 minus BK minus 2. You will get. Why? Because an element here it will be BK minus 2 minus AK minus 2. So that is the reason I have written like this. Now here I'll get A2 minus B1 minus A1. Clear? Now whatever may be the intervals in between, I'll write first element and the last element of the interval. Fine. I'll continue this symbol here, greater than or equal to. This will be the value of this length of an interval. Fine. After simplification, I'm going to get this value n is equal to 1 to infinity length of in as bk minus a1. So in general, I can write this will be greater than b minus a. Whatever may be the suffix value, it should be greater than b minus a. Fine. Now I can rewrite this statement as n is equal to 1 to infinity length of in is greater than or equal to will become greater than directly. If this is greater than this value and again this value is greater than b minus a, so I can directly write this expression with this. Again, we know from the definition of length of an interval, I can say this as length of in. Fine. Now I can rewrite the same statement as, I'll just rewrite, see here, length of in is less than, I'm reversing the inequality. Fine. Just reversing the, suppose if you have a less than b, when you reverse it, b greater than a. Similarly, when you have a greater than b, when you reverse it, b less than a. Same length of in, I can write this as which is less than n is equal to 1 to infinity length of in. Am I correct? Now, as per the property of translation invariant, look at the equation 2. This is from the translation invariant, right? Now, see here, I have obtained an expression length of in is less than or equal, less than n is equal to 1 to infinity length of in. Now, from equation 2, I can rewrite this as length of in is less than n is equal to 1 to infinity length of sum of all the lengths, which is again less than or equal to measure of that particular interval plus epsilon. From equation 2, I can say. Hope it is clear. I have used equation 2, that is property of translation invariant, in the next step. Fine. Now let me continue with the theorem. Now since epsilon is arbitrary value, anyhow it is very small, so we can neglect this value. After neglecting, I can write length of in is less than or equal to measure of I. Clear? Now let me take this as equation 3. I am just repeating the steps once again. See here, I have chosen randomly an elements from the open interval which is inside the closed interval. Fine. In such a way that considered element will be in between the last values of the interval. Fine. So if you go on continuing this process, that should the process should ends after certain number of repetition, say k. So I have chosen an element b in last interval, say ik. See here, b in last interval ik, such that this element is in between last values ak and bk. Fine. Clearly n is with reference to closed interval, which is the highest value, and I have chosen an open interval which is inside the closed intervals. So I have chosen open interval in closed within inside the closed interval. So this is the smaller compared to largest value. Here I is with reference to open interval and n is with reference to closed interval. So this value is always greater than this value. Now I have ordered all the lengths of an open interval. So I can write bk, first value with the last value I can write bk minus a. Anyhow, whatever may be the suffix values, I can write b minus a. b minus a will be length of the particular interval in. Fine. I have combined this with the last element, or else I have rewrite the same equation so as to get length of in is less than length of in, summation n is equal to 1 to infinity. Fine. Now I have used equation 2. From equation 2, I have used the property of translation invariant so as to write m star I plus epsilon. Since epsilon is arbitrary, I can neglect this. I will get m star of I here. Let me say equation 3. Now look at the equation 1 and equation 3. See here, length of in is less than or equal to m star I. Here equation 1 is length of I is greater than or equal to m star ab. M star ab, equation 1 can be written as, see here, m star of ab is none other than length of an interval in, right? Is less than or equal to length of I. Am I correct? See here, the same thing I can write this as reverse. See here, length of in is greater than or equal to m star of in. Fine. Now combine this equation with this. I can write length of interval is equal to measure of a interval, whatever may be the I value, suffix value, length of this particular interval from these two equations, third equation and fourth equation. I can write length of an interval is equal to measure of I. Hope it is clear. Now this is only when a considered interval is closed interval. Fine. Since the theorems are very large, it is nearly 2 to 3 pages, but the concept is simple. Please try to understand. Fine. Now I have proved the first case for a closed interval. Now we have to prove the same for an open interval. Let me prove the case 2. Case 2. Case 2 is when I is open interval. I'm sorry, I'm trying to skip the statement. I'll send you the notes, so I'll just skip the statement, you just listen to me. So when I is open interval, then as per the definition, there exists epsilon greater than 0, which is very small, such that some j will be subset of I. In the sense, j is one of the interval which is inside this open interval I. Fine. So by using monotonic property, or else I can say, since I is one of the set and j is within that, obviously length of j will be less than, length of j is less than length of I. But remember, when you keep on removing some of the elements in I, this first interval I, this will become very small compared to j. Meaning is, I can write length of j is greater than length of I when we remove certain epsilons or certain values. Fine. So if you keep on remove, I can write length of j is greater than length of I minus epsilon. Fine. Now I'll reverse the inequality. I can write length of I minus epsilon will be less than length of j. Length of j is none other than, by using the definition of an outer measure, I can write m star j. Fine. Now I'll just rewrite again. Length of I minus epsilon is less than, length of j is none other than measure of j. Fine. Again, since j is subset of I, in the sense I can use monotonic property, right? J is less than I can write. When you apply measure, m star of j is less than m star of I. Fine. So I am using the same property. I can write m star of j is less than or equal to m star of I. This is something like an expression a less than b less than c. So I can write, see here, suppose if I have a less than b less than c, I can write a less than c. So that is what I have written. This expression is less than m star of I. Now as per the definition of measure, m star of I is none other than length of an interval I. As per the definition, m star of I is none other than length of an interval I. Since I have added length of an interval with certain epsilon value, whatever may be the value added, this is length of an interval I, right? As per the definition. So this value is always less than length of I plus epsilon. Why? Because in this element, or else I can say in this term, we have an extra term epsilon, but here we don't have. So clearly this element will be less than this element. Why? Because we have an extra term epsilon. Fine. So I can write m star of I is less than or equal to length of I plus epsilon. Fine. Now since epsilon is arbitrary, so I can neglect epsilon on both sides. So epsilon is arbitrary. I have neglect that. So this expression will become length of I is less than measure of I, which is less than or equal to length of I. What I have done is I have just neglected epsilon value. Fine. Now I can clearly write m star of I is equal to length of I. Why? Because let us consider the first expression. See here, length of I is less than or equal to measure of I. Fine. Second expression, when you're going to consider, measure of I is less than or equal to length of I. The same expression I can rewrite as reverse. Length of I is greater than or equal to m star of I. Now look at this expression and this expression, one with less than or equal to inequality and another with greater than or equal to inequality. So by combining this with this, I can write length of an interval is equal to measure of an interval, or else measure of an interval is equal to its length. This is what we have to prove. I am repeating case 2 once again. I have considered for open interval, then there will be an epsilon greater than 0 such that some interval j is subset of I. In the sense, I am considering one of the interval within the set I. So if this is the case, I can write j is less than I by using monotonic property. Now I am applying measure on both sides, so I can write this expression. I will use this further steps. The same statement I will be using in the further step. Now clearly length of j will be greater than length of I minus epsilon. Why? Because if you keep on removing an element from I, again it will become smaller compared to j. Fine. So I can rewrite this expression, if a greater than b, I can write a less than b or b less than a. See here, something like if a greater than b, I can write b less than a. That is what I have done here. So length of j is none other than measure of j, as per the definition of measure of a outer set. Fine. Now length of j is measure of j. Again I am using this expression, measure of j is less than or equal to measure of I. So that is what I have written here. The same step. See here, first with last expression I have chosen. Again I have added some epsilon value to length of I. Why? Because measure of I is none other than length of I. Since I have added epsilon to length of I, this value will be smaller than this value. Why? Because I have added certain value to length of I. And now epsilon is arbitrary constant. I can eliminate that. So thereby I am getting length of I is less than or equal to measure of I, which is less than or equal to length of I. Now let me consider first two inequality. Next, followed by the rest of the inequality. So from those two inequality, I can say length of an interval is equal to its measure. So that is what we have to prove. Go to the statement. See here, outer measure of an interval in R is equal to its length. That is what I have proven. Length of an interval is equal to measure of an interval. This is first case for open interval. Now I have proved for the second case. This is for first case is for closed interval and second case is for open interval. So therefore, in both the cases, the outer measure of an interval R is equal to its length. Hope it is clear. Thank you. Continue in the next section. So the theorem may look somewhat lengthy, but keep on practice. You may feel easy later on. See you in the next session.